Hello and welcome. This video is for the 2024 Ohio Stormwater Conference. This presentation is on microplastics, their environmental and human health impacts, and the current state of remediation research. My name is Taliesin Haw. I'm an Americorps member serving at the Cuyahoga County Board of Health through NowCorps, a program of Tinkers Creek Watershed Partners and Serve Ohio. Plastics, what we know, what we don't, and what to do about it. We'll try to cover as much as we can in answering the following questions. What are plastics? What are their health impacts? How can we remove them? And what is already being done? First, we'll define the sources, types, and life cycle of plastics. Plastics are an example of induced demand, an industrial waste material rebranded as a miracle invention. They're produced for free by the oil industry as a byproduct of oil refining, uses heat to break down fossil fuels into different grades that are used for different types of applications, including naphtha, an oil residue that all plastics are made from. It might have been treated as a pollutant if not for excellent marketing. Production is still increasing today, so what's happening to all of it? Well, its fate somewhat depends on the polymer type. There are 7 different categories of plastics. They serve different purposes. Some can be recycled cheaply, most cannot, and are either incinerated or else enter eventually into our watersheds and ecosystems. Storm events especially bring significant plastic waste downstream into the oceans. Types 1, 2, 4, and 6 are typically accepted by recycling centers. Types 3, 5, and 7 are not accepted by any industrial recyclers. Some of these are also made from highly toxic volatile organic compounds like vinyl chloride, which you might remember from last year's accident in East Palestine, Ohio, where a train operated by Norfolk Southern failed and overturned, and then was quickly incinerated, which created even more volatile organic compounds. Less than 9% of all plastic waste is recycled. The rest enters the biosphere, including all sampled animal, plant, and human tissues in recent studies. Plastics get into our air, water, and waste pathways. Plastics primarily enter the oceans through the world's freshwater systems, making our watersheds and lakes the front line of defense for our global ecosystem. So that's the global situation. But our region is actually the largest plastic producer in the most petroleum productive continent in the world right now, with much of that happening through our watersheds. 10,000 metric tons of plastics enter the Great Lakes every year. Most of that travels at some point through Lake Erie. If you see a correlation between microplastic flows and the presence of harmful algal blooms, that's because buoyant microplastics can actually act as a habitat for microalgae, exacerbating our lake's recurring harmful algal bloom problem. Now on to their human health impacts. We're really only starting to look into this. Most of the research is from the past decade or two. Plastics don't exist in a vacuum. They often come with other, more harmful chemicals attached. These include EPA-regulated industrial toxins like PFAS, BPAs, dioxins, and most regrettably, phthalates. Phthalates like Teflon and other anti-stick waterproofing sprays are among the most notoriously harmful of these plastic-carried materials, with known endocrine and developmental impacts. You might notice that these plastics exacerbate some of our air's greatest health risks. Macroplastics, which are big enough to see, leach chemicals. Microplastics, which are smaller than a mite, contribute to blood clots or thrombosis. And nanoplastics, well, they're small enough to be in all of our bloodstreams right now, exacerbating issues like anemia. This is one of the reasons it's taken so long to understand which compounds are negatively impacting health. Altogether, these affect many aspects of human health, including increased risks of cancer, harm to the nervous system, heart and lungs, and on the hormonal or endocrine system, impacting reproductive, growth, and developmental cycles, meaning these can be disruptive to fertility and childbirth. But that's not all, folks. Let's talk for a moment now about nanoplastics. Nanoplastics are so small they can freely enter and leave the circulatory system, inserting themselves in between cells and interfering with the normal transfer of chemicals across cell walls. They correlate with cardiovascular issues, including thrombosis or blood clots, and anemia or deformation of red blood cells, and they're detectable in all species studied so far. Let me say that again. Nanoplastics are found in all animal and plant tissues sampled. So then, what do we do about it? Can we remove them? And if not, how can nature learn to deal with this? Well, there are several ways available. Obviously, the best and easiest answer is to stop buying them. Moving on from that, they can be filtered, broken down chemically, or left to slowly disintegrate. Let me explain a few of these terms on the left. Biosequestration is when plants, fungi, or microbes capture and isolate the materials from the rest of the ecosystem. Phytoremediation is when plants use various techniques including enzymes and solar radiation to break down recalcitrant chemical bonds. Nanomaterials covers a lot. Some nanomaterials might end up being useful for filtration or sequestration of some of these forever chemicals. For macroplastics, filtration is by far the most popular option. Many rivers around the world have systems installed like the one pictured here in the UK to capture the plastic before it enters the open oceans. It's most effective for watersheds facing a high pollution density. Each of these forms of degradation listed here have a place. None of them, though, work for every type of plastic. Some species even produce chemicals that are especially effective at degrading certain plastics. This is an active and exciting new field of research that we don't really have time to get into during this presentation. But to give a taste, some materials, like dioxins, which don't break down under any normal conditions and can remain as contaminants for decades or centuries, for those, we can look to bioremediation for specialized enzymes that are produced by fungi or archaea, which can actually break them down into simpler and less toxic forms. More research needs done in cultivating these toxin processing microbial communities. When bioremediation isn't an option, though, often the best we can manage is sequestration. Many times, this isn't one solution, but part of a process or a cycle of combined solutions. Once a toxin has been sequestered, if we can't recycle it, and combustion carries its own risk, at least we can reduce the damage these toxins would do by protecting as much of the environment as possible from direct exposure. All things decay, but some take minutes and others thousands of years. This molecule here, this is one of the ones left for us by Norfolk Southern. It's also an ingredient in Agent Orange. The 4 chlorines on the left and right, colored in green, they're what make this such a volatile organic compound. And figuring out how to process dioxins is one very interesting current application of bioremediation. Heavy metals, volatile organic compounds, and persistent organic pollutants are concentrated and stored in certain plants. This bioaccumulation is a critical tool for repairing our ecosystems. Sunflowers, dandelions, duckweed, and some Solanaceae, the family of plants including tomatoes, nightshades, they all show remarkable phytoremediation potential. Phytoremediation is a complex topic in itself, but suffice to say, plants are our best bet for managing industrial pollution, for several reasons, but mainly, they're tough. Plants can generally handle microplastic exposure far better than animals, and microplastics bind easily to them in many natural environments. The experiment pictured here was carried out in a laboratory setting, but the results would suggest duckweed can help sequester wetland microplastics. In some situations, the presence of microplastics actually seems to accelerate phytosequestration of other harmful toxins like heavy metals. Finally, some good news. So, what is the state of remediation research right now? Research on this topic is growing quickly, but still, plastics have been around for more than a century and we're just now starting to really look at their health impacts. Nanoplastic research methodologies are still being developed. This is an issue of which we understand far too little, and the long-term impacts upon our global biosphere's ability to adapt to other crises is still unknown. For us in Northeast Ohio, we are establishing long-term monitoring of microplastic concentrations in Lake Erie and some of its rivers. Our department also works to educate communities on health. We talk with refugees and immigrant communities to make sure they're aware of the risks of eating fish from the lake. We work with local watershed partners to do cleanup events. But our main way of improving plastics in our watersheds is the forest canopy restoration work and outreach with communities to become stewards of nature themselves. The healthier an ecosystem we have, the more resilient it will be to any industrial pollution, including microplastics. Solutions really are as diverse as their locations. For example, the photo on the upper right here actually isn't a physical barrier, but a wall of air bubbles that allows fish and boats to pass through while blocking plastic waste. In the Caribbean and Southeast Asia, they put nets across critical rivers, and here in the Great Lakes, you might say we're catching up. Get it? Catchment? Water treatment plants were never designed to address this type of pollution at all. Northeast Ohio's water treatment system, for example, only removes about half of microplastics and very little of the nanoplastics from the water supply. There is currently no way to eat, breathe, or drink water without consuming significant microplastics. More research needs done. Novel approaches, both industrial and ecological, must be prioritized. Water infrastructure needs to be updated, not only to improve reliability and capacity due to climate change and century storms, but to filter a growing number of industrial toxins. Plastics are now a permanent part of this world. We can start by finding out what that means. So let's try and do better. Nobody wants to eat this for dinner. Thank you, and feel free to contact us for more information at the Cuyahoga County Board of Health. And don't forget to check out our references linked below. No, really, there's some great references here.